So
Okay,
our next speaker is Emin. He's an associate professor at Cornell University and the founding director of the IC3. He's been building OSs for quite a while, and since then he's been building blockchains. Most currently, the CEO and co-founder of Avalanche, building a fresh design of a cryptocurrency platform. So Gun, the screen is yours.
Okay, well, thank you very much, Itai. And Sarah is always a very difficult act to follow, but I'll try to have a nice interactive conversation today about consensus protocols and try to situate you with regard to where we are in the evolution of various different protocols, what people have done in the past. So what is consensus? Maybe that's the starting point that we should launch off from. So anytime you have a distributed system, one often finds almost anytime one often finds oneself in a situation where you want to have them have the distributed ensemble of nodes take coordinated action. You would like them to take something, to decide on some action to take as an ensemble, and this requires what is informally known as agreement. We all have to decide, all of the nodes that comprise a system have to decide that something indeed happened. Itai sent this message. This node has now crashed and we have decided to cleave it out of our network. These are the types of things that are part of almost every distributed system. When today you go to Facebook, there is a consensus mechanism behind the scenes saying these are the front end nodes that are currently up to which we could direct a user. When you go to check your Gmail, there is the exact same process going on. And also in the background, there is a set of nodes that house your data. And again, there's a consensus protocol that says Itai had the following mailbox, and now he had this message deposited into it. And that all typically requires some amount of agreement among a set of nodes that are cooperating to provide a service. So you might think, well, okay, this is indeed a common thing. I have seen many distributed systems before, and I can appreciate the need for them to agree on things that happen, for them to take action as a unified Unitarian entity. Instead of a whole bunch of discombobulated nodes, each with their own separate state. I would like them to implement a single state machine. So that's a very common thing to find oneself doing. And you might think this is easy. Okay, I'll just come up with something. I'll just have one node tell everybody, or, and I'll call that Solana, or, I'll just come up with some crappy little system for, keeping things in check. And you will often, not often, you'll pretty much 100% guaranteed find yourself devising something that is short of a consensus protocol that is properly spec'd for the environment it's operating in. So it's incredibly important to understand what these protocols are for, what their properties ought to be, and what the design criteria ought to be, and what the design choices are that are available to us. And what I want to do during this talk today, if as much as I have time, is go through the design choices and situate you and give you an overview of the last 45 years of consensus protocols and where they left us. Okay, so the thing that's going to make our lives very, very difficult in what would otherwise be a simple task is the fact that these nodes are separate entities operating with their own essentially state, if you will, coupled with the fact that they can fail. So at any one time, you can lose some of these nodes and they can come back up having forgotten what happened. And that suddenly puts you in a very funny position of altogether building a state machine that's correct, that implements a coherent machine, while individual components that comprise that state machine can fail and come back up. So consensus is a fundamental building block. It's encountered in just about every setting. And there are separate problems from consensus. Information dissemination is not consensus. I have a transaction, I have to get it out to people. That's not something that requires consensus. It's just dissemination. I'm just spreading it out. I can say anything I want. The sky is green, the sky is purple. I can say these things, and getting this word out kind of like, getting a megaphone in one's hand and saying in incoherent things at a street corner, that is not something that is just information dissemination. It's a much simpler process, a much simpler problem than consensus. Consensus is when you, me, and all 60-something people on this call all together have to decide that we shall endorse, let's say, we shall leave the EU today. Did we leave the EU? Did we not? Well, we decided on whatever we decided, and that is now the law of the land. Okay, so that's a very different process than just saying whatever any node likes. So it's different from information dissemination. It's different from replication protocols. There is no primary in charge in consensus protocols. I'll get to the formal definition in a second. But in the normal problem setting, there is a set of, let me see if I can write here, set of n nodes, which are comprised of some correct and some failed nodes. I should put F here. So this is C union F, and I have n of these nodes that comprise my system, and they together have to take an action. And none of these nodes are, at least initially when the protocol starts, in a distinguished position. So I don't have a natural leader. I don't have a natural entity in charge. If I have one of those, I have a problem that is not a consensus problem. I have a much simpler problem. I should solve that, and that's going to be easy. The replication, for example, it's not information dissemination. It's similar to it, but not exactly yet. And replication is a different problem. Primary backup protocols are a different problem. And today Solana is making some noise. Look into the protocol carefully, and you will see that it's simply a replication protocol. It cannot tolerate failures of the designated leader or Byzantine behaviors by the designated leader. So then what do we have in the typical consensus setting that is a very general problem, very commonly encountered, and quite fundamental to blockchains? Well, so we have, what do we have? We have a set of nodes n. Some of these are correct, and some of these are failed. Okay, so that's what we're starting with. And what should the system do? Well, it should possess some properties, and these properties are typically one of three. So the very first property that is very crucial is going to be agreement and safety. So what does that mean? It means that every correct node, when it decides on some value, on value Vx, decides on the same value, decides on Vx equals Vy, equals this ultimate value decided by the system. So what's the saying? This is kind of verbose for saying the obvious thing. If I, as a participant to the system, believe that something happened, we took action to leave the European Union, then everybody else that's part of the same group as me also believes the same thing. Itai, who's also a correct, nice guy, part of the same ensemble, does not think that we're still part of the EU. He applies the same tariffs as I do. He applies the same policies as I do. So this is a safety requirement. There exist no two nodes that have decided different things. Okay, so there are no traces of execution on any two nodes that differ in some decision. A second property that typically these things will want to do will be a progress property. Sometimes it's a termination property, but sometimes termination is impossible in consensus protocols. You can't quite guarantee termination. In settings where failures are quite benign, then you can have a termination property. But more often than not, there is a progress property that you want, and sometimes expressed as a liveness property. And these come in all sorts of different variants, actually. So the one that I happen to like best, or whatever I have seen most, that is a little loosey-goosey actually for actual work, is to say something like a system must make progress whenever it's possible to do so. So what does that mean? well, it leaves a little bit undefined. Is there a better way to say this? You know, so sometimes it's expressed as eventually all correct nodes must decide on a value. And that's sufficient to say that the system takes concerted coordinated action, because coupled with the safety property, if I decide on a value and you decide on a value, well, by property one, we'll decide on the same value. So this is typically something that you see. By the way, if you look around on the internet, you will notice that a lot of these properties are expressed really badly, really poorly, and quite often incorrectly. Almost every node must have the modifier correct node in front of it, because the incorrect nodes can do anything that they want. And the third property that people typically add is non-triviality. So you don't want somebody to give you a protocol whose decisions are always the same decision. Like, they shouldn't just be like, well, I decided on 42. At this time step, I decide on 42. No matter what happens, I decide on 42. Is that safe? Of course. Is it live? Yes, of course. And this is the kind of thing that academics really get, of course, tangled up in. And but so we just ruled it out. So the value decided must be must be one of the proposed values. So so you can't just bake something in to your system. So this gets us to the sort of the desiderata for a consensus protocol. We would like it to be safe. We would like it to be live and alive. We would like the ensemble to be live. So this is kind of important and subtle as well. So sometimes people get very confused, especially database people, by the way, especially distributed database people, about where their system lies. The systems that we are talking about, or when I say the system, I mean the boundary around the nodes that comprise my ensemble. I do not mean any single node. Any single node can fail. I do not mean a subset of nodes that can fail. Those things can happen. They are of no material concern to me. As a system implementer, I care only about the boundary. This is important because there will be other people out there, especially people from a database background, who will tell you that there is something called a cap theorem, who will tell you that the cap theorem says that you cannot have a safe and live system at the same time. Those people are completely deluded and they're just muddled thinkers, okay? So we're going to talk a whole lot about systems that achieve both safety and liveness. And the cap theorem is an entirely an exercise in getting confused and tangled up in one's own definitions. Okay, it does not have the implications that most people think it does. I'm happy to go into the cap theory discussion at some point. It will take me at least half an hour and get me worked up a little bit, which I don't mind getting ranty about technical issues, but it will derail us. So let me get into consensus protocols. But put aside anything and everything you might have heard on the internet about the cap theorem, about impossibilities claimed by various internet people. So those same people go and log into Gmail every day, and they use a consistent and an available system every day. Okay, and there are some trivial impossibilities, but if I put that aside, it is quite possible to provide both safety and liveness under well-defined circumstances for any system that for many practical systems people will care to build. Okay, so this is our starting position. This is what we would like to do. We would like to build a way of sending messages that if I follow that way, that method, that protocol, at the end, I have these safety, liveness, and non-triviality properties upheld. And what else do I need to worry about? Well, I do need to worry about a little bit about the setting. So what do I really mean by that? Well, the first thing that I need to worry about is node behaviors. So so what are the sort of the ways in which my nodes can behave and work are pretty important, and they will determine just how complex my protocol needs to be. So okay, you might say that's good. So what are the different ways that nodes might behave? An interesting way that nodes might behave is, this is again, academics have been through this space for many decades now. And there's, for every single behavior, there's a name and so on and so forth. But there are three that are kind of important. One of them is known as the fail-stop model. Another one is known as crash faults. And another one is known as Byzantine. So fail-stop means that when a node is about to die, it notifies the rest of the world that it's about to die and then dies nicely. So that's a very nice behavior to have if you can have it. It's very useful for, when you want to sort of make progress and assume the best sort of scenario for what you're about to build. In reality, we do not have fail-stop failures, right? When I just lost my cell phone a second ago, and it just died on me. I wasn't expecting it. It certainly didn't announce its death. It could have. I could have perhaps made it fail-stop, but I wouldn't be guaranteed to be fail-stop. In reality, what happens is we deal with typically crash faults or Byzantine faults. You have crash faults when the only behavior available to a node is behave as prescribed and then stop. And you have Byzantine faults where the node is unconstrained in its behaviors. If those of you who've studied Byzantine history, you know that they did crazy stuff back in the day, collude with their enemies. There was a queen who got her son killed by her daughter's husband, for example. So these are really extreme behaviors that they were quite capable of. So in real life, we will be either dealing with crash faults where a node is, these typically happen when I can say something about, when I can constrain the behavior of the node. What's a good way I can do that? Well, for example, if all of the nodes are under my control, then I know that my nodes are as trustworthy as me. And if I'm compromised, then the entire thing is compromised anyway. So it makes sense to operate in the crash fault setting. So you encounter this there. So single operator. So all of Google's systems, for example, are designed for crash faults. They're not designed for Byzantine faults. Well, maybe the all might be too much, but the majority of Google services are designed under the crash fault assumption and not Byzantine. But another interesting way in which you can get crash faults is if you constrain the nodes to operate and use some special hardware. So Intel SGX, for example, gives you this ability where the nodes are constrained to operate either as prescribed or they can stop. But even the node operator is not allowed to change the code in the enclave inside the protected execution engine inside the chip. So crash faults and crash fault tolerant systems are interesting whenever we have a single natural entity in charge, or when we have special hardware like SGX available to us. In the general setting, we have Byzantine nodes, and these are nodes whose behaviors are completely unconstrained. They can do anything and everything. The blockchain space is typically a Byzantine setting. There are multiple operators. In fact, every node ideally is operated by a different entity. And each and every one of them can change the code any which way they like and can send you any kind of unexpected message at any time. So they're completely unconstrained in their behavior. The next thing that we should worry about before we go on to design some protocols is the network behaviors. And so there are three different assumptions that one can make. One of them is synchronous, the other is partially synchronous, and you guessed it, the third option that I can have is asynchronous. In fact, there is quite a lot more that I could have, but here is what these mean. So let me see if I can draw this. You guys can see the drawing that I'm making. I don't know why it's this terrible green color. Let's pick this nicer color. Okay, so imagine that this is my histogram of packet timings. If all my packets follow a histogram kind of like this, a lot of them are very fast or maybe like that or what have you. As long as this is a straight line. As long as there is a straight line up here, this is delta. As long as there's a straight line within, so there's a time period within which all packets are guaranteed to be delivered, then we call that system a synchronous network. And we call that network a synchronous network. So this is very nice. Why? Because then if I send you a message and I wait for 2 delta and I don't hear back from you, I can say that, well, I sent a message to Itai 2 delta ago. That would have given me enough time to hear back from him. I didn't hear back from him, and therefore he may have died. Okay, so synchronous systems are pretty nice because they have this nice property, and this time-bound delta allows us to build systems that respond to this known bound. The partially synchronous version of this says there is a delta, except we don't know what it is. So I will send messages to Itai, and he'll come back within, whatever, some time period, but I don't know the delivery speed of the underlying network. I don't know the delta itself. And that is a slight twist, and it changes things. It can change things quite substantially. There are other histograms possible. So here's a histogram. Let me draw a different one. And this is an interesting one. Mathematicians, when they say asynchronous, they typically have a notion like this. So this is a histogram of message or of packet delivery times. If you look at this, it's a long tail distribution. The average of this is infinite. So the network, the time it takes for an average packet to be delivered is very, very, very high. On the other hand, most of the packets are delivered very fast. So this is actually quite a good approximation, I would say, of the internet today. I think it's a much better approximation than a synchronous model. And it's in fact a more interesting setting than the partially synchronous setting. Because the partially synchronous setting, I can come up with adaptive schemes to find the bound and so forth. So, regardless, it's an interesting domain to be in. And in some settings, when you hear people talk about asynchronous, they'll be referring to this. In others, especially those people from a computer science proper background, as opposed to a math background, they really just mean something entirely different. They just mean this big question mark. That is, there is a histogram, but they want to make no assumptions whatsoever about it. Some packets you send, they can be locked down for a long time. Some packets you send, they get locked by lockdown. Some packets can get delayed for a long time. Some packets are delivered immediately. You never know what regime you're in. So this is kind of important. If something works well in an asynchronous setting, that's good. The fact that something doesn't work in an asynchronous setting is not a problem. And this is something that trips up quite a few people, even experts in this space. So asynchrony essentially means I am unwilling to make any realistic assumptions about the real world. And if by it's a way of saying I'm tying my hands behind my back. If I can do amazing things after having tied my hands behind my back, I'm in a great situation. But the fact that I cannot, for example, write legible stuff after I tied my hands behind my back doesn't mean anything whatsoever. Okay, so the impossibility results in asynchronous settings, yes, they're significant. Yes, they have intellectual value beyond belief. Yes, they're very, very interesting. But for practitioners, they are quite often overblown. So I'm going to get back into this maybe if I have time, but at this rate, I'm going a little slowly. Let me speed up. So let me just give you the last 45 years of consensus protocols in a nutshell. So given this setting, what I'm going to focus on is going to be Byzantine nodes upholding safety and progress guarantees with non-triviality in networks that are asynchronous. Okay, so that's what I want to focus on. And there have been quite a few, in fact, hundreds of consensus protocols proposed, but they fall into 3 categories. And these three categories are as follows as of today. For about 35 years, we had classical protocols. And that work was followed on by Satoshi Nakamoto, who came in and said, in fact, okay, so we'll talk about, let me make the network behavior undefined for now. I'm going to switch between synchronous, partially synchronous, and asynchronous models as we go along. So Nakamoto came along and he said, look, all of this academic work on classical protocols, it's interesting, it's great, it's nice, it's just completely not applicable to blockchains, to open wide deployment on the internet, and I'm going to redefine the problem and go to a different definition for safety. And along the way, I will achieve amazing things that are not possible with classical. And he did that, and that was a big breakthrough, an amazing breakthrough. The people behind this framework, the classical framework, they have Turing Awards, Leslie Lamport and Barbara Liskov. They did fantastic ground setting and set the stage for the next multiple decades to follow. Nakamoto, he doesn't have a Turing Award. He probably has 1 million BTC. And then there is this, which is a different approach, and it uses one of the insights from Nakamoto, but couples it with different mechanisms. So let me talk to you about how these protocols work and what their properties are as a result. So let me see if I can I move this down? I can't. Let me create a new sheet. Let's take the case of a node, of somebody who wants to coordinate some nodes. Let's see, can I make this a little bigger? Yeah, that's good. So I have some nodes up here, and I would like to take some decision. It turns out that some of these nodes are Byzantine, okay? So these guys are pretty evil. And they will say things. They will say and do all sorts of terrible things. And I have no constraints whatsoever on what they are going to do. And so my job now is to somehow make sure that this ensemble right here, where is my black here? Okay. That this ensemble here, all together as a singular entity, takes coordinated proper action. And what I need to do is define a protocol. Now everybody knows what a protocol is, and typically the protocols will consist of two components, a read protocol and a write protocol. So I want to have let me define a write protocol for taking action. I'm an entity outside here. I'm this person right here, and I would like this entity as an ensemble to remember the fact that we're leaving the EU. And I will propose, I don't know how other people have been doing this on Zoom calls. I'm not sure how interactive we can get, but feel free to chime in. Let me propose the following protocol to you. We're going to start with the simplest possible thing, and we're going to recreate the last 45 years of research, slowly at first and more quickly towards the end. So I want to take action, and I will define a write protocol and a read protocol. So I would like the ensemble to act as a decision-making body, kind of like a Senate. And I'm the proposer here. And I would propose to you, here's my write protocol. My write protocol is that I have a write set of one node. I write to this node. And my read protocol is I read from one node. Would this make a good protocol for running my country? Nobody's chiming in. I actually don't know if anybody's allowed to chime in.
No.
No, somebody chimed in. Thank you. This would be a terrible protocol. Why? Because I would write to this guy that I left, and this guy would read from another node, doesn't know the fact that, I would write to this node that that there is a new decree passed, that I would like to leave the EU, and his consent is sufficient for me to think that we left. And then this guy asks this fellow, and he'll get a different response. We just violated safety. So clearly, this write set was terrible. It was too small, and it kept me from making whatever. It allowed me to make progress. That was really nice, but I ended up thinking that we left, and this guy did a query, and he ended up thinking that we did not leave. So this violated safety. So what's a good next step? Well, here is a proposal. What about changing this protocol so that I don't write to one guy? So let me go to the other extreme. I was writing to one guy. Obviously, he was reading from a different guy, and there was not enough of an intersection. Why don't I change this protocol to be like that? What about now? Have I made progress? Do I have a good protocol in my hands? In the classroom, when I look expectantly at the classroom, kind of like this, it actually usually gets a response. So I'll sit here quietly. Who was it that spoke last time?
It was me. I would say no again.
Again, so who's this? What's your name?
My name is William.
William, why do you think this is a bad protocol?
I think maybe it would give the person writing too much power.
No. This was a simple system that you know I didn't really set the stage very well for my problem, but just imagine that this is just recording whatever the first client says. Okay, so it's not the goal of these people is not to vet what should happen. They should simply make sure that safety and liveness, safety and progress guarantees are upheld. So as long as they say the same things to everybody, we're going to be okay, right? And so,
Well,
so
I
that,
think node crashes.
thank you. And I feel like I know this. Well, who's this?
This is Dara.
Oh, okay, Darren. I don't know you. Nice to connect. Okay, you're right. So Darren is pointing out the big problem with this. The problem now is I went to the other extreme. And so if I am trying to write to all of these nodes, and I'm waiting for responses to come back from each and every one of them, then you will discover that I'm actually in a bind. I put myself in a bind. This fellow who's red, he is failed. He may be failed, you know, without out of his control, or he's a bad guy. He's not going to respond to me. And if my protocol is collect answers from all n, well, it works. It upholds safety as long as I can collect answers from all n, but it doesn't make progress when it's possible to do so. It's possible to make progress in the presence of a small number of participants, it turns out. But I'm unable to make progress in the presence of a single failure. A single failure means that I don't collect acknowledgements from n people, and therefore my write cannot succeed. And similarly for reads, my reads are not going to succeed as long as there's a down node. The system is down. This is a terrible system I built yet again. So I went from no safety but live to you know to I guess great safety when it's achievable, you know, when it happens, but the system doesn't really work, and just a single fault takes everything down.
And also very poor efficiency even when it does work.
Also what?
Poor efficiency because you.
Power efficiency is terrible. That's true. That's true. So I didn't get into any other additional properties for consensus. Typically, the three that I mentioned are all that people try to achieve. There is fairness. There is energy efficiency. There's a whole bunch of other things that one could worry about. Ease of coalition forming. So these are all things that one could worry about, especially in the blockchain setting, that I'm not concerned about at the moment. But you're absolutely right. So, so what should I do? Well, I think you will find that if my job is to maximize the ability to make progress and ensure that conflicting messages are not sent, what I need to do is come up with a way of maximizing the benefit I get from the intersection between the write and the read sets. Okay, so what does that mean? Well, so I will come up with a protocol for writing to some set of nodes. Why am I unable to write? I will write to some set of nodes, and the reader will read from another set of nodes. There will be an intersection right in the middle over here, and some of the entities in the intersection may be faulty. And despite them being faulty, it will be possible for this fellow to hear the coherent right answer, the right message. So if you think about it, you will find that the following scenario of W equals 2/3 N and R equals 2/3 N is a pretty darn good setting for dealing with failures up to 1/3. Okay, so what does that mean? So the protocol then consists of this node writes to every node once again, but waits for acknowledgements from this node writes to all N nodes and waits for acknowledgements from 2/3 of the nodes in the set. And this guy does the same for reads. So that ensures that there will be an intersection. Why? Because the write set is greater than half and the read set is greater than half, and therefore there has to be an intersection. How big is that intersection? Well, the intersection of 2/3 N with 2/3 N is 1/3 N. Okay, so I can tolerate up to 1/3 N minus 1 failures. So I can tolerate, I can tolerate having this guy be evil, having that guy be evil, having that guy be evil, having that guy be evil. Even in this eventuality, I can handle the case of this guy doing a write. He's writing to all these nodes. It doesn't matter what he does to the red nodes. They're evil. They will lie to him. But this reader, as long as he follows this quorum protocol I just outlined, he is guaranteed to hear from this set. And this set has up to about 1/3 of the entities in it evil, but not exactly 1/3. It has 1/3.
We have about 5 more minutes.
I will sum it up very quickly. So that means that that there will always be some correct node to carry the message from me onto him, saying the latest decision we made, what we are not in the initial state anymore. We took an action, and Gun said that we're leaving the EU, and this guy is then notified. So this is an interesting scenario, and so this is going to be at the root of all classical protocols. Now, there are a couple of implicit assumptions here. The big implicit assumption is I know all of the entities in the network. So if it turns out that the world was kind of like this, that you thought that this is how big the world was, and I thought the stuff to the left over here was where the world was, my intersection properties will just go out the door. I will write to all N that I think are part of the Senate, that I think are part of the ensemble. You will read from your worldview, which is a different one from mine. It's this one. And our intersections now are no longer guaranteed to have a correct node in them. So now we might suddenly end up having an intersection that looks kind of like this, or what have you, like this, an intersection that looks like this that has only evil people in it. So it's essential to manage membership, and this is the reason why Satoshi came up with the protocol that he came up. Now, I want to give you one additional set of graphs. If I look at probability of a safety violation, and this is the number of nodes that are Byzantine. So this is not N, this is B. As B tends towards N, the probability of a safety violation goes like this. If there's a single evil node in the system, the chances of that node subverting this quorum system that I just built are absolutely zero. And this goes on for a while until the 1/3 point. And at the 1/3 point, after the 1/3 point, the probability of the attacker taking over is 100%. Okay, so that's a very bizarre situation. If I look at the probability of liveness, okay, so on this axis, I'm going to look at P live. So then I see that as long as the number of failed nodes is less than 1/3, the system is live. As soon as the attacker has 34 out of 100 nodes, then the system is no longer live. He can keep the system from making progress because he controls 34 messages, and every writer is waiting for 67 responses. Therefore, they will never get that 67th response. The system is effectively down. So this is a pretty stark reality, and this 1/3 bound is a very important one for classical systems. Now, I want to take maybe a minute to tell you about Avalanche. I'm going to skip Nakamoto. You have seen it, or you will have seen it every which way, and Itai will probably talk about selfish mining at some point and the various attacks against Nakamoto consensus. But I want to tell you about life and the universe in a different setting, in the Avalanche setting. So in Avalanche, what we do is we change the safety criteria to be probabilistic, just like in Nakamoto. So we're not going to require that every correct node take the same decision. We will change it to every correct node with very high probability. Now, every correct node with very high probability means it's possible for safety to be violated, but it'll be so infrequent as to be as infrequent as hash collisions, or the probability of all the oxygen atoms around me migrating to the far corner of the room, leaving me with, surrounded in a bubble of nitrogen, and I could suffocate. Could that happen? It can easily happen with Brownian motion. But the probability of that happening is actually very, very, very small, too small to really be worried about. And the way Avalanche works is not by nodes asking other nodes for their decision, but by doing small repeated rounds of polling. So in Avalanche, what the node does is it says something like, okay, there's a decision to be made between red and blue, and there are some nodes out there that are blue, and there are some nodes that are red, and so what we will do is we want everybody to come to the same color decision. So this node that is currently undecided will pick a small number of other nodes to poll. So it's going to ask, hey, what color do you prefer? What color do you prefer? What color do you prefer? And at the end of this process, it's going to itself change its own color to pink. In the next round, he might do the same. He might pick 3 different nodes, and so on and on and on. And the interesting thing about the Avalanche protocol is that the math works out and says that this simple process of polling a small set and changing your color in response to the majority of the poll will yield a unified unitarian decision. It will yield a decision as hard as an ensemble taking a decision with support from 67 members out of 100 participants. In the previous protocols, everybody had to talk to everyone else. In this protocol, you're doing repeated tiny amounts of sampling. So what does this mean? Well, it means a whole bunch of things, and they are kind of interesting. And in the last minute, I want to just talk about Avalanche's safety and liveness with respect to other protocols.
We're really out of time, Gon. If you
1 minute,
keep this
maybe.
short, please.
Very
1 minute.
just 1 minute. Because of the way Avalanche works and because of its probabilistic properties, the probability of a safety violation is never going to be 0. It's going to be slightly above 0. But when the threshold is violated, after which the Byzantine attacker has, has control, has let's say 1/3 control of the network, the system has graceful degradation, which is one of the key properties that people should seek for, don't know to seek for, because it hasn't been possible. If the attacker has control over a larger subset of the network, then Avalanche's guarantees of failure every 10,000 years go out the door. But they don't go out the door to the point where the attacker wins immediately. They go from a failure every 10,000 years to a failure every few thousand years, to a failure slightly more often than that, to a failure every few hundred years. And at some point, okay, well then that's when the attacker begins to have almost guaranteed chance of winning over the system. But that line is way over the 1/2 line. So the attacker typically has to have enormous compromise to succeed for sure on an Avalanche network. And that's a very interesting situation to be in. Conversely, there is a different line, and I'm not going to get into it. There's a liveness line that's on the other side that one can separate out into these two different curves. And the protocol designer has great leeway in how they choose the parameters for an Avalanche system, such that they can build a system that's efficient, and achieves quick finality while also navigating this very nice flexibility to tolerate large numbers of attackers. I think I should wrap up there, and I hope this gave you a very, very high-level overview that was somewhat informative on what we want out of a consensus protocol, why the simplest measures don't really work well, and what one needs to do in terms of achieving intersection, and maybe a glimpse into how Avalanche and other systems are different from classical.